Okay, so this short video tutorial is on kinetic energy. What is kinetic energy? Well, the definition, we'll get to the definition in a second, but kinetic energy can be loosely defined as the energy associated with motion. All right, so the energy associated with motion. We sometimes can call this moving energy. All right, so the word kinetic, if you think about kinesiology, it's talking about motion and moving, so we can think about kinetic energy as the energy associated with motion or moving energy. What is this definition? Well, it's defined as the work needed to accelerate an object. So it's defined as the work needed to accelerate, I'm going to underline keywords here, an object of a given mass from rest which is 0 meters per second, to, I'll underline the word rest, to another speed. Okay, so this is the explicit definition where we say that it's defined as the work required to accelerate an object of a given mass from rest to another speed. So you take an object from 0 and accelerate it, and we know that takes energy, right? And since work is explicitly the transfer of energy or the change in energy, we know that energy is required to accelerate this object. So the symbol for work is W, symbol for acceleration is A, for mass is M, starts from rest, that's our V1, to some other speed, V2. So again, just to put some variables to that, because we're going to use those a little bit later. All right, what is kinetic energy dependent on? Well, just thinking about it, EK is dependent on a couple factors. One such factor that it's dependent on is the speed of the object. Now, clearly, this makes sense. All right. An object that's moving faster will carry more kinetic energy than an object that's moving slower. But it's not just dependent on that, because I could have two objects like a turtle and a transport truck. And if they're both moving at the same speed, many of you would argue that the transport truck would have more kinetic energy than the turtle. And you'd be correct. And so what's the difference between the two of them, besides one's an animal and one's a truck, is that the mass of the object. All right, the mass of the object. So we're going to say that EK is dependent on the speed of an object and the mass of an object. And the question is, what is that relationship? Some other things. We can infer that if you increase the mass of an object or increase the speed of the object, this will in turn increase the kinetic energy of the object. Likewise, if we decrease the mass or decrease the speed, we'll decrease the amount of kinetic energy. Just a relationship, so we can, a little hand-waving argument shows that this is likely the case based on what we know. All right, now for the fun. We're going to do a little derivation. So derivation of the EK equation. So let's quantify this. Let's quantify the value for how much kinetic energy an object carries based on its speed and its mass. We're going to start off with the work equation. We know the work equation in general form looks like this: F delta D cos theta. Now, we're going to assume that the object is being forced or pushed with a constant force in the exact same direction as the displacement, delta d. If that's the case, if it's pushed parallel with it, that means that the angle it makes is 0 degrees. Cosine of 0 degrees is equal to simply 1. So this term is going to drop to 1. If it drops to 1, then we know that it results in this simplified equation. Work, we can calculate the work by just taking the force multiplied by the displacement of the object. We also know this. We also know that work equals, and we know it's the transfer of energy, like so. And that's given by delta E. All right, so that's the transfer of the energy in that object. Well, what do we do from here? Well, let's figure out what we need to find out the speed and the mass need to be a part of this equation to figure out what the kinetic energy is or how much work is done. So what we're going to do is we're going to start with this equation. And we can see clearly that we don't want to know delta D, we don't have delta D, and we don't have the force. But we know a couple things. We know from Newton's second law that force equals, everyone just said it, mass times acceleration. So if force equals mass times acceleration, and there's a F here for the force applied to the object, that means that we can take this relationship m times a and substitute it right there. Substitution is a very powerful technique in mathematics and in science to get new relationships for variables given some old variables. I like to call this the MAD equation. So work equals MAD, mass times acceleration times delta D. Well, we've got an acceleration there and a delta D, which is not speed and which is not just mass. We have the mass there, but we don't have the speed. So we're going to do one other thing. We know by definition of acceleration, it's the final speed minus the initial speed divided by the time. Well, now we've got some speeds in here. So it's starting to look a little closer to a relationship with speed and mass. So I can substitute that in. And what we get, the MAD equation becomes m v2 minus v1 over delta t times delta d. All right, I'm going to do a little math thing here. Since this division, everything on top is multiplied and the bottom is division, we know that this delta t can simply just get moved. And it's not really moving anywhere, but we can rewrite this in the exact same fashion like that. This doesn't change anything. If you plug in numbers here and calculate it and plug in numbers here and calculate it, you get the same result. Why did I do this? Well, I did this because I still have a delta d and delta t. I want only things measured in terms of speed and mass. So we've got speeds and mass, but we've got this other term here that we don't like. But what is delta d over delta t? Again, probably many of you said, simply the average speed, distance over time. Well, if we know the average speed, what's another way to write the average speed? Again, many of you probably said, add the two speeds, divide by 2. So I just rewrite this out. Good. Now, speeds, mass, we're doing great. Now the one thing I want to point here is that just like we move this delta t to be under the delta d, which doesn't affect anything, it's still, if you calculate it, I put in the numbers and divide it, you get the same result. I'm going to do something here. I'm just going to move this 2 to be under the mass, just to get these terms more in line with one another, like so. All right. Now what we're going to do, a little bit of some math wizardry here. It's not really math wizardry, it's a very simple technique. You can call it FOIL if you want, first outside, inside, last, or you can call it, clearly we can see this is the difference of squares for those of you that are good at math and see that relationship right away. So we're going to multiply this term by this term, this term by this term, this term by this term, and this one by this one. I'll expand that. All right, so when we do that, we get the work done to accelerate an object from speed 1 to speed 2 is given by the mass over 2, v2 times v1, v1 times v2, doesn't matter. Remember that 2 times 3 is 6, or 3 times 2 is 6, so it doesn't matter which way I write this. Then I've got v2 times v2, so that becomes v2 squared. Then I have minus v1 times v1, which is minus v1 squared. Then I have minus v1 times v2. Now what you'll notice here, and this is why those of you who have seen this as a difference of squares, is that right here you can see that v1, v2, subtract v1, v2, or 2 times 3 minus 2 times 3 is just 0. So they cancel out to 0. All right, I'm going to just move this up here so we can finish this off nicely. All right, so those two terms cancel out, and what are we left with? M over 2 times v2 squared minus v1 squared. All right, so we've basically almost got our solution. The only thing I'm going to do now, just to simplify this, we've got only mass and speeds in here, which is exactly what we wanted. This is the amount of work required to accelerate a mass m from this speed to this speed. That's it, because we started from the work equation over here. Just did some substitutions to see that that is the exact same thing. And we could have done all the work over here, but we didn't have information or variables, so we've got this derivation here. Work, remember, is also equal to the change in energy. So work is the change in energy. So the amount of energy that's added or changed by accelerating the object from speed 1 to speed 2 is given by this quantity here. All right, I'm just going to expand this bracket. I'm going to write the delta E over here. So the change in energy, or the work. Remember that these two things are identical. They are the same. Just a different way of writing it. So I'm going to multiply the brackets in. So it's m v2 squared over 2 minus m v1 squared over 2. Now what do we have? Change in energy. That means in this case we're talking about kinetic energy, so I'm going to write a subscript k on both of these terms. You can do that too. What this means now is that this term here is your final EK, or what we call EK2. This is how much kinetic energy the object has at its final speed of v2. And then we subtract how much the initial EK was, EK1. So if we know how much initial kinetic energy it has and how much final kinetic energy it has, if we subtract them, we can figure out exactly how much energy was required to accelerate that object to that new speed. Let's say this is 10 units, and this is 2 units. 10 minus 2 is 8. So we've got 8 units of kinetic energy, or sorry, 8 units of energy is required to accelerate the object from whatever speed that was to that new speed. Okay, this equation is extremely important. So I'm gonna write it just below here and put a box around it. So you can write this on a sheet somewhere nice and big. This is a key equation. And if you want, you could also put the word, you could write W equals change in kinetic energy, the final kinetic energy minus the initial kinetic energy. So clearly we can see that this term here represents the kinetic energy, that term there. So, but if we look back to the definition, it said EK, the kinetic energy, is defined as the amount of energy it requires to accelerate an object from 0 to some final speed. So, by definition, we're going to set v1 equal to 0 in that equation, and we're going to make v2 just equal some speed v. All right, it doesn't matter because we don't need a subscript v2. We're just going to say at some speed. Well, if we set v1 equal to 0, this term right here is gone. 0 squared is 0 times anything is 0, so we're subtracting 0. So what we end up with is this kinetic energy equation of m and V2 became just V squared over 2. And there is our kinetic energy equation. So if someone asks you, or if you're asked at some point, what is the kinetic energy of an object moving at 20 meters per second with a mass of 1 kilogram? Okay, so you would say, all right, if I'm looking for the kinetic energy of 20 meters per second with 1 kilogram mass, what you'll notice is that it was accelerated from 0. So it's really saying, assuming it was accelerated from 0, how much energy would it have at that point? Well, 20 squared is 400, times 1 is 400, divided by 2 is 200. All right, that's it. So we've got two very important equations. The amount of work, or the change in energy required to accelerate an object from any speed to some new speed, and the amount of energy required, and then the kinetic energy equation, which is just how much energy does an object have at a specific speed, assuming that it was accelerated from 0. You can see here that what if an object slows down? How much work is done? Well, if an object slows down, V2 is smaller than V1. If this quantity is smaller than this quantity here, you get a negative value, which means it takes negative work to slow an object down. Okay, so that makes sense too. It takes work in the opposite direction, or the negative work, required to slow an object down. That's the same thing as coming up here to our original equation and saying, oh, the angle isn't 0, the angle's 180. And the cosine of 180 is -1, so we would get negative work. All right, so we're going to try the examples next. Go back and review this note just to make sure that you really get it, and make sure that you write out the note as well. It's also posted online, so if you want to get the note from online, you can also get it from there.